when Galileo turned his telescope onto planets and was able to observe that they are rocks, they are matter, no more or less spiritual than the planet Earth. This was a fundamental revolution in our understanding of what the universe was. When Copernicus showed how much simpler it is to understand the universe if one thinks of all the planets and the Earth rotating around the sun, rather than everything rotating around the Earth, this was also a fundamental revolution in people's conceptions. Then people applied this understanding to larger and larger entities. Gravity works so that if you have a bunch of, let's say, a gas of material here, and it ends, so there's a roughly defined order to the gas, what's going to happen is the gas and the outer particles over here, the outer side, will be pulled in towards the center by all the mass in the middle. And the gas closer towards the center will be pulled slightly outwards by the material here, but much more towards the center because there's so much more in the center. What happens, therefore, is things tend to agglomerate into something like spheres. And that was used as a theory to explain how the sun originated, how the planets originated. And when you look and you see galaxies are essentially billions of stars held together by gravitational attraction into spherical shapes or shapes that are more oblate. And you then apply it to the next scale and you find that there are galaxies close to each other, clusters of galaxies which seem also to be clustered in together by the same force of gravity. And you extend this further and further out and you get to a structure of the universe, the physical universe, which seems to be determined by the law of gravity. Very, very, very simple law with very interesting consequences. Now, there were some problems with this conception of the universe because if you had all these galaxies or planets or whatever in the universe, would they not tend to also clump into the middle? And they would collapse into the center eventually over many, many years, and they would form a big black hole, and there would be no universe left. And if the universe was infinite in time, then that would have already happened at some time in the past. So why is there a universe? So Newton was aware of this problem, and he tried to come up with reasons why an infinite universe would be stable. But this was a problem that remained until Einstein's time. There's another thing that's problematic with that kind of a theory, and that's what it neglects. When you're trying to figure out what is the structure of the universe, and you're not taking into account anything other than gravity, are you leaving something out? For example, human beings, love, life, meaning, purpose, spirituality, art, literature, philosophy. Are those important somehow to describe the universe? Or are those just incidentals that arise out of a naturalistic universe? Humans arise, and the natural activity of humans is to engage in those kinds of things. Or is that something fundamental to the universe, something that tells us something basic about the universe, and if our theories of the universe don't take it into account, maybe we're missing something very fundamental. Now, there are scientific problems with defining all of these terms. First of all, we want to have a theory of the universe. What is the universe? Well, is the universe an entity? It isn't really. It's like a set. There's no such object as the universe. There are entities. Our mental conception, when we think of all these entities together, we group them and we say, this is the universe. But there's no such thing as the universe. Can we have a scientific theory of the universe? Scientific theories, by definition, take many repeated events and study the regularity and the patterns that develop, make predictions, make experiments, verify them, and so on. You can't have many universes. You can't have many originations of the universe. So some people don't even like the term scientific theories of, let's say, the origin of the universe, because it's not scientific in that sense. However, it is possible to make predictions. For example, if there had been a Big Bang, there would be certain radiation permeating the universe coming from all directions as a result of that explosion. And in fact, Mantis and Wilson a number of years ago discovered that radiation. And that gave strong experimental backing to this theory of the Big Bang.
Is there a name for that kind of radiation?
Yeah, it's the microwave background radiation. Microwave background radiation. It's 3 degrees Kelvin. In fact, I think Arno Penzias is maybe some observant or something.
He's a fun guy. His kids are PhD.
Yeah, so I mean, it's another example where somehow the people affiliated with some theory certainly don't think that their theory has anything counter-religious implications, but other people hijack it somehow. Now, on the other side of the coin, where the universe was considered to be eternal, Einstein's theories also blazed the way to show a resolution of that, and that brings us up to the Big Bang Theory. Now, the origin of the whole idea of the Big Bang Theory starts with human beings looking at the universe and trying to figure out what is it made of, how large is it, when did it begin, why is it here? And again, that has always been the case. Probably as long as we've been able to think and see, and as long as there have been people who wonder about deep questions, people have looked up and seen the stars and wondered what they are, and how you get there, and does somebody live there, and so on. And in ancient times, the approach, for example, of Aristotle was more metaphysical, philosophical. In modern times, we have a somewhat different approach. We have science, which attempts to come up with equations that can be proven rather than speculations. And again, of course, what happened was that people said, wow, this universe is a mechanistic one. It's a naturalistic one. It's not spiritual entities moving in perfect circles because they are the perfect geometrical shape. But this beautiful geometrical shape comes out because of beautiful equations, which have these tremendously aesthetic results. But it's some kind of a natural law. People began to think of the universe more as a machine, clockwork mechanisms, laws, simple laws really regulating what happens. Then people applied this understanding to larger and larger entities. Gravity works so that if you have a bunch of, let's say, a gas of material here, and it ends, so there's a roughly defined border to the gas, what's going to happen is the gas and the outer particles over here, the outer side, will be pulled in towards the center by all the mass in the middle. And the gas closer towards the center will be pulled slightly outwards by the material here, but much more towards the center because there's so much more in the center. What happens, therefore, is things tend to agglomerate into something like spheres. And that was used as a theory to explain how the sun originated, how the planets originated. And when you look and you see galaxies are essentially billions of stars held together by gravitational attraction into spherical shapes or shapes that are more oblate, and you then apply it to the next scale, and you find that there are galaxies close to each other, clusters of galaxies, which seem also to be clustered in together by the same force of gravity. And you extend this further and further out, and you get to a structure of the universe, the physical universe, which seems to be determined by the law of gravity. Very, very, very simple law, with very interesting consequences. Now, there were some problems with this conception of the universe, because if you had all these galaxies or planets or whatever in the universe, would they not tend to also clump into the middle? And they would collapse into the center eventually over many, many years, and they would form one big black hole, and there would be no universe left. And if the universe was infinite in time, then that would have already happened at some time in the past. So why is there a universe? So Newton was aware of this problem, and he tried to come up with reasons why an infinite universe would be stable. But this was a problem that remained until Einstein's time. There's something scientifically, though, missing in that theory. What is that theory about? That theory is about the matter in a pre-existing universe. There's an infinite universe, eternal, and in it there is matter, And gravity kind of dictates how that matter will interact with each other. But what about the universe itself? What about that which all this matter is within? Without having a theory of that, you don't really have a theory of even the material universe. And that's where Einstein steps in. Modern science has extended that kind of investigation, and through Einstein's theory has come up with a way to understand some of the basic conundrums.
What is like the correlation between gravity and magnetism?
Well, it's not. Magnetism is a separate force, and we tend to think somehow when you talk about magnetism, we tend to talk about things attracting by magnetism. So we think of anything that's attracting, we say magnetism. But magnetism is a very specific force, and gravity is a totally different force. And this is all gravity. There is magnetism, but magnetism has nothing to do with our being attracted to the Earth. It's gravity, or the moon being attracted to the Earth. Now we'll get to the first part. How do the galaxies form and so on. Once there is something rather than nothing, and this is now a scientific question, why is there something rather than nothing? Why there was it? Sure. And space and time, space is expanding. There's initially just energy. Energy coalesces into matter. Remember I mentioned that matter and energy are really just different faces of the same thing. And you have this matter. Now again, there are more subtle implications of the theory, modern implications of quantum field theory, and the vacuum. There's no way that I can go into that. If people are interested, there's literature for the educated layperson. You don't need a physics background for that. But basically, you have energy turning into matter. Space is expanding. As it's expanding, things are cooling down. This tremendous energy is getting cooler. It's kind of filling a larger space, so it's kind of cooling down on average. And it's starting to coalesce and clump because of gravity. Now, the reason gravity does this is not because gravity is so much stronger. Why does gravity win out over everything? Why does gravity dictate the size and nature of the universe with interactions? We know that there are, for example, electric forces, magnetic forces. Why is it gravity does this? The answer is very simple. Electricity, we know, comes in two versions. There's a plus, what we call plus and minus, right? Electrons and protons. Overall, in any given volume of space, there's billions and billions of electrons and protons, but there's the same amount. So they cancel each other kind of. On the small scale, where there's more protons here and more electrons here, there's strong electric fields here, very much stronger than gravity. In fact, the strength of electric fields is 10 to the 40 times the strength of gravity, which is a number that doesn't make any sense. It's so huge. It's a billion times stronger than gravity. But overall, once you get beyond the atomic dimensions and so on, molecular dimensions, those forces cancel each other because there's just as many electrons as protons and other positive and negative particles. Gravity has only one type, only one charge. And therefore it doesn't cancel out, just the opposite, it aggregates. So the more mass, the more stuff, the more energy, the more gravitational attraction. And it just goes on out there forever, getting weaker and weaker, but as you go out, there's more and more stuff. So it gets weaker and it gets stronger at the same time. Now, this matter is locally aggregating into roughly spheres or ellipses and so on. And those separate ellipses and spheres are kind of aggregating into clumps and clusters near each other. The general scientific understanding, for example, of the formation of the solar system, is that you would have a gas of material of dust particles, and it's spinning, and you know from a centrifuge the heavier stuff will spin out towards the side, and it'll clump together and form planets, and the hydrogen and helium in the center will clump together, and that's the sun. And that's an overgeneralization and simplification and so on, but roughly something like that. Really, the heavier elements come from the interiors of stars that formed previously and then exploded, spewing out their material, and the planets originate from second-generation material. Material that was formed already in stars that were purely hydrogen and helium and exploded and spewed it forth, and then the second generation formed the planets and so on. Again, there's so much written about this.
I have a question. When you explained it very well, what causes the circular motion? And you gave the example of a rocket or something being fired at a very high speed, being attracted to the body by gravity. What is the force when somebody doesn't fire it? What is the force that goes this way rather? This is gravity.
Again, we had the formation, the scientific understanding of the formation of the planets. Things which were moving around and didn't have a high enough speed crashed into the center. The Earth is full of craters and pockmarks. Look at the Moon. The Moon has tremendous craters because it doesn't have an atmosphere, so whatever came to the Moon actually landed and smashed into it. The Earth has an atmosphere, so things burn up. We see all the time falling stars. What are they? There's matter coming down to the Earth and burning up.
What is the force? What is that force?
So whatever originally in forming, let's say, the solar system, that matter that clumped together that didn't have enough speed to take it around in orbit crashed into the sun. Only those things which had the right speed when they were swirling around and moving and coalesced at the right speed, those things ended up in orbit. In other words, they don't. It's not something like a rocket which has an engine moving the force. They initially had a speed in that direction of a certain amount. And it was just the right speed so that they ended up not crashing into the sun and not escaping from the sun, but exactly the right speed to take it in orbit. Everything else crashed into the sun or crashed into the planets. In the Newtonian and Galilean universe, we had many stars, many galaxies, and they were spread maybe in an infinite extent throughout the universe, and they'd always been there. And we can understand through gravitational attraction not only how they were clustered together and how they were moving, but maybe even how they formed. If you had a dust of particles of atoms of material, then gravitational force would cause them to coalesce slowly in towards each other. If you have a gas here and it kind of tapers off, so you have like a cloud, then the material at the edge of the cloud will be pulled in by all this mass inside. Everything at the edge will be pulled in by the large amount of mass inside it. The material a little bit further in will also be pulled out by the outer edge, but much more by the majority of the mass which is inside. And therefore things tend to coalesce into spheres or ellipses, and that's why, in fact, the sun is basically spherical, the Earth is basically spherical, even the galaxies are spherical or elliptical. So this force of gravity was able to explain the shapes of planets and stars and galaxies, and the arrangement of the solar system, and even the clumping together of galaxies. Many galaxies, even though they're separated by large distances, would clump together, and we can see that with our telescopes. And it's all due to the force of gravity. Again, as a little aside, why is it that the force of gravity is so strong that it can cause such tremendous effect at such large distances? What about electricity? What about the electric force? Does that affect anything? The answer is very simple. We all know that there's an electron and a proton. There's a positive and a negative, so to speak, charge. And in any given space, in any given volume, any amount of material, there's the same amount of electrons and protons altogether. They're arranged slightly asymmetrical, so that when you get to a small enough space, you'll find a little bit more of the positive here, a little bit more of the negative there, and therefore there's very strong electric fields. And the electric field there will be billions and billions and billions of times stronger than the gravitational field there. But overall, they cancel each other out on a larger scale because there's an equal amount of plus and minus. But gravity has only one type. And therefore, the larger the amount of mass or energy, the more gravitational pull. And it goes out far. And the more stuff there is further away, the more it contributes, and you get this tremendous force.
I just want to get back to the balloon with the different dots and the expansion of this balloon in the circle. In other words, a constant motion, this constant motion, and the galaxies. Now, all these galaxies, debris, what are they comprised of, first of all? And then when you were trying to tie in, not that you tried, you did tie in the distance with the time. The further the distance from the time, there was an acceleration of time. Does it ever change? And at what point in this description that you gave, does it constantly expand? And at what point in this expansion does that Big Bang explain the beginning of the universe?
Okay. Now we'll get to the first part. How do the galaxies form and so on. Once there is something rather than nothing, and this is now a scientific question, why is there something why little was it? Sure. And space and time, space is expanding. There's initially just energy. Energy coalesces into matter. Remember I mentioned that matter and energy are really just different faces of the same thing. And you have this matter. Now again, there are more subtle implications of the theory, modern implications of quantum field theory, and the vacuum. There's no way that I can go into that. If people are interested, there's literature for the educated layperson. You don't need a physics background for that. But basically, you have energy turning into matter. Space is expanding. As it's expanding, things are cooling down. This tremendous energy is getting cooler. It's kind of filling a larger space, so it's kind of cooling down on the average. And it's starting to coalesce and clump because of gravity. Now, the reason gravity does this is not because gravity is so much stronger. Why does gravity win out over everything? Why does gravity dictate the size and nature of universal interactions? We know that there are, for example, electric forces, magnetic forces. Why is it that gravity does this? The answer is very simple. Electricity, we know, comes in two versions of the plus, what we call plus and minus, like electrons and protons. Overall, in any given volume of space, there's billions and billions of electrons and protons, but there's the same amount. So they cancel each other out. On the small scale, where there's more protons here and more electrons here, there's strong electric fields here, very much stronger than gravity. In fact, the strength of electric fields is 10 to the 40 times the strength of gravity, which is a number that doesn't make any sense. It's so huge. It's a billion times stronger than gravity. But overall, once you get beyond the atomic dimensions and so on, molecular dimensions, those forces cancel each other out because there's just as many electrons as protons and other positive and negative particles. Gravity has only one type, only one charge. And therefore, it doesn't cancel out, just the opposite, it aggregates. So the more mass, the more stuff, the more energy, the more gravitational attraction. And it just goes on out there forever, getting weaker and weaker, but as you go out, there's more and more stuff. So it gets weaker and it gets stronger at the same time. Now, this matter is locally aggregating into roughly spheres or ellipses and so on. And those separate ellipses and spheres are kind of aggregating into clumps and clusters near each other. The general scientific understanding, for example, the formation of the solar system, is that you would have a gas of material of dust particles, and it's spinning. And you know from a centrifuge, the heavier stuff will spin out towards the side, and it'll clump together and form planets. And the hydrogen and helium in the center will clump together, and that's the sun. And that's an overgeneralization and simplification and so on, but roughly something like that. Really, the heavier elements come from the interiors of stars that formed previously and then exploded, spewing out their material, and the planets originate from second-generation material. Material that was formed already in stars that were purely hydrogen and helium and exploded and spewed it forth, and then the second generation formed the planets and so on. Again, this is so much written about.